Today, we are bringing an isolated Unix machine online as a fully functional, connected TCP IP network node. Completing this requires a four-step sequence: configuring the physical interfaces, establishing name resolution, setting the routing tables, and initializing the network daemons. Before we start typing, you need three things ready to go. You must have root access to the machine, a mapped-out IP address scheme for your network, and a solid familiarity with the command line. Walking through this sequence step by step ensures you dictate how data enters and exits the specific system. Step 1 is defining the physical hardware. We do this by assigning an address to the local network interface using the system's boot files and the core ifconfig command. Alongside the IP address, we have to define a netmask. The netmask looks at the entire range of available IP addresses and logically divides it into localized subnets. Look at this split screen. On the left, you see the plain text variables placed in your network startup file: the interface name, the IP address, and the subnet mask. On the right, you see how those variables translate into the active command that configures the hardware. Once the command runs, you verify it by checking the interface status. You are specifically looking for the up and running flags to confirm the physical link is active. Setting this interface and netmask correctly is the foundation that allows the system to determine whether a packet belongs on the local network or if it needs to find a gateway. Static/etc/hosts files are difficult to maintain as a network grows. To make name resolution scalable, we use the named daemon to handle dynamic IP-to-hostname mapping. The etc/named.boot file follows a specific structure. The daemon relies on these highlighted declarations. Directory sets the working path, while primary and secondary define exactly where the server gets its authoritative zone data. When the named daemon starts up, it reads this file line by line. It uses the primary and secondary zones to answer local queries directly and forwards any unknown external requests out to the broader internet. Delegating this process to a dynamic daemon removes the need to manually update host files across your environment every time a machine moves. Now that the node knows its own address and can resolve names, it needs a path to the outside world. This requires setting up routing to direct traffic destined for external networks. For a simple network, you can establish a static path right from the terminal. You use the command route_add_default, followed by your gateway name and a metric, directing all unknown traffic to exit through that specific router. If your network has multiple routers and changing paths, a single static route will fail. For complex environments, we initialize the gated daemon to handle dynamic routing protocols. The gated configuration file enforces a strict mandatory order. You must place definition statements first, followed by protocols, then static routes, and finally control statements. Reversing this order prevents the daemon from starting. Within that structure, enabling a specific protocol is straightforward. Under the protocol block, typing rip yes activates the routing information protocol, allowing your node to learn paths from neighboring routers. By locking in these routing tables, every packet leaving your interface has a defined path to its destination, rather than dropping into a void. At this point, the node can communicate, but it isn't offering any network tools. Having the separate service daemon running constantly for every tool, like FTP or Telnet, consumes memory and processor cycles even when they aren't in use. The solution is inetd, the Internet superserver. Instead of running 20 independent daemons, inetd runs as a single process. It listens for connection requests and spawns the specific service daemon only when it is actually needed. Looking at this diagram of the etc/inetd.com file, a single line dictates exactly how a service behaves. It maps out the service name, the socket type, the protocol used, the wait status, the user permissions, and the specific program arguments needed to execute the request. When you make edits to this file, you have to send a hang-up signal using kill-hup and the process ID to force inetd to reread the configuration. With inetd running, your node becomes a responsive server, providing tools like FTP without a constant resource drain. Even with a correct configuration, connections can drop. The most reliable way to locate the failure is by using the inside-out ping methodology. Start by pinging the loopback address, 127.0.0.1, validating the internal TCP IP software stack. Step 2. ping the local IP to confirm the physical network card works. Step 3. Ping the gateway, verifying router connectivity. Finally, pinging an external hostname tests DNS and external routing. As you run these tests, the specific error messages identify the root cause. A connection refused message means the connection was successful, but the remote host is simply not running the requested service. An unknown host message indicates a DNS mapping issue, while network unreachable indicates that the routing tables lack a path to the destination. By isolating the specific failure point from the software stack outward to the internet, you can accurately target your fix. You have assigned a physical interface, established name resolution, built the routing tables, and initialized an efficient superserver. To prove the configuration, initiate a remote login to a neighboring host. When that terminal resolves into a blinking cursor prompt, your connection is verified. You have now configured the core services of a Unix TCP IP node, establishing a stable foundation for this machine.